We would like to also measure the feature redundancy. Now, redundancy of feature is nothing but the information which is conveyed by a feature is the same just like another feature which is present in given data set. So here we have multiple measures or to measure the similarity of information or contribution of information given by a feature. First type of measure is correlation-based measure. Second is distance-based measure, and we have other coefficient-based measures. Let us understand and see what is correlation-based measure. So correlation-based measure is a linear dependency with a measure for identifying the linear dependency between two random variables. Say for example, I have feature 1 and feature 2 and I need to identify whether they are correlated or not. That means increasing one is having what effect on another variable's value. So here we calculate something called as Pearson's product moment correlation coefficient, or simply it would call as Pearson's correlation coefficient, which is given as rho coefficient of f1, f2, coefficient of feature 1, feature 2 divided by square root of variance of feature 1 into variance of feature 2, where covariance between feature 1 and feature 2 is calculated as summation of feature 1's value at particular data point I minus feature 1 mean, that is f1 of I minus f1 bar, multiplied with feature 2 at particular data point I minus mean of feature 2, that is f2 of I minus f2 bar. This will give me covariance between feature 1 and feature 2. I would call it as covariance f1, f2. Now, how to calculate variance of feature 1? Variance is calculated summation of f1 of I minus f1 bar whole square. So, this is nothing but feature 1 data points value I minus its mean, that is f1 bar. Mean is calculated as summation of all data points in a given feature divided by n, which is nothing but number of data points. Similarly, variance of f2 is calculated as summation of f2i, feature 2 value at some particular data point, minus feature 2 mean, f2 bar whole square. We will add them and I will get f2 bar as summation of all data points in feature 2 divided by number of data points, that is n. So this will be f2 bar will be 1 by n summation of f2i. Say for example, we have feature 1 aptitude and feature 2 as communication. If I want like to calculate its Pearson correlation coefficient, I want to find out whether they are having some correlation or not. Increasing one value whether decreases another, or increasing one value also increases another, or they are irrelevant of each other. I have to find out with the help of Pearson's correlation coefficient. So you can calculate f1 with f1 bar, with f2 I can calculate f2 bar, and with these values I can calculate f1 minus f1 bar, and another column as f2 minus f2 bar. I can sum them and call them individually as variance of f1 and variance of f2. I can multiply these two columns and sum them and call it as covariance of f1 and f2. And finally, I can divide covariance by square root of variance f1 into f2. I leave this calculation of given data set to find out Pearson's coefficient up to as an exercise. Let us discuss value of correlation. What value I would get as an output of Pearson's correlation? So Pearson's correlation value can range from -1 to 1. Value 1 of correlation gives perfect correlation. That means both of these features are perfectly correlated. If value of Pearson's coefficient is 0, we say that these features are not in relationship or they are independent. They are not redundant. If value is -1 or -1, then we say perfect negative correlation. That means increasing one feature value is decreasing another feature value, which is ultimately giving us same information. So then we can consider these two features in this case also as redundant features. So here we adopt something threshold value which can decide an adequate similarity. Say for example, I will consider all features which are having value positive or negative 0.8, more than positive or negative 0.8, then it will be considered as redundant features. Otherwise, they will be treated as non-redundant features. Distance-based measure. If I have two different features and I would like to find out their distance, we use first basic distance as Euclidean's distance. Now, Euclidean's distance is calculated with the help of Euclidean's formula, which is called as distance from feature 1 to feature 2. That is, d of f1 comma f2 is square root of summation 1 to n feature 1 minus feature 2 of particular data set whole square. We calculate feature 1 and feature 2 are the features in our n-dimensional data set. How to calculate Euclidean's distance? Say for example, again I have an aptitude F1 and communication F2, feature 2, feature 1 and feature 2 respectively. I will calculate their difference, that is F1 minus F2 row by row, and this will give me all data points difference. I will first square them to avoid all negative values. So I will take square of F1 minus F2, which will give me the last column. Now this last column is taken summation of, and that summation is then taken square root of. And that square root will be giving me the Euclidean's distance between two features. Again we set some threshold value and we will consider only those features as redundant which can have more value than given threshold value. So this is how we make use of Euclidean's distance. But there do exist other type of distances apart from Euclidean's distance. That distance is called as Minkowski distance. Now this Minkowski distance is same as Euclidean's distance, but the only changing formula is instead of square root, it takes arc root. And within this square root, instead of taking square root difference of terms of features, we take arc power of a given set of differences. So basically, if I substitute value 2 of r Minkowski distance formula, I will ultimately end up in having Euclidean's distance. That's why we can say Minkowski distance with r is equal to 2 is same as Euclidean's distance, which is also called as L2 norm. Likewise, we have third type of distance that is called as Manhattan's distance. Manhattan distance is calculated with the help of Manhattan formula, where we do not take any square of distances and later on summations no square root is taken out. So we take square root with one power, that means no square root is there. How to avoid the negative term which calculates the difference between these two? So we take modulus of set of differences of data points. So d of f1 comma f2 is summation over I is equal to 1 up to n data points, difference of f1 minus f2 I in modulus. So this is same as our Minkowski distance with r is equal to 1. That's why they are also called as L1 norm. Whenever we calculate Hamming distance, it is an example of Manhattan distance. Let us discuss third type of other coefficient-based measures. So apart from correlation and distances, we have something different coefficient-based measures. First coefficient-based measure is Jaccard index. Now this Jaccard index is calculated or measuring the similarity between two features as J is equal to N11 divided by N01 plus N10 plus N11. Or Jaccard index or Jaccard coefficient method will only work out when we have binary type of values in our features. So if feature doesn't have binary value, then we cannot calculate its measure using coefficient based method of Jaccard. Anyways, let us come back. Let us say our feature is having only binary values. Now binary value can be either 1 or it can be 0. So we have to calculate number of data points where both features are having value 1. That is what we call as n of 1, 1. Number of data points where we get both feature value as true value. Divide by number of data points where we get first either of one feature as 1. That is, I can have first feature value 0 and second feature value 1 plus, or I can have first feature value 1 and second value as features false, or I can have both of these value as 1. That is n of 1, 1. I will add up all those number of data points and I will take its ratio. And that ratio is called as Jaccard index or Jaccard coefficient. Now using this Jaccard coefficient, we calculate something called as Jaccard distance. Jaccard distance is finding dissimilarity between two features. Remember, Jaccard coefficient or Jaccard index is measuring similarity, while Jaccard distance is measuring dissimilarity. Dissimilarity of feature is calculated as complement of Jaccard index or coefficient. That is nothing but D of J is equal to 1 minus Jaccard index. That is 1 minus J simply. Let us calculate Jaccard index for a particular feature. Say for example, feature 1 is a binary feature, can have either value 1 or 0 for a particular data point. Likewise, another feature F2 is also binary feature, can have values from 0 or 1. So I will calculate number of data points where I have both values as 1. So I have only 2 data points where both features value is 1. So my N11 will be equal to 2. Next, I will calculate all those data points where either of feature is 1. That means I can calculate feature with 0, 1 value, 1, 0 value or 1, 1 value. So as you can see, 1, 2, 3, 4 and 5 data points are there where we have total where either of feature is 1 or both features are 1. So we can calculate n of 1, 1 as 2 and n of 0, 1 plus n of 1, 0 plus n of 1, 1 is equal to 5. So the Jaccard index will be 0.4. So I can say feature 1 and feature 2 are 40% similar. And how much they are dissimilar? That is D of J, Jaccard coefficient is calculated as 1 minus 0.4, that is equal to 0.6. They are 60% dissimilar. Another coefficient based measure is simple matching coefficient, that is SMC. It measures the similarity between two features, which includes those cases where both features are having value 0. Remember, in Jaccard, we are only interested in only those features which were having true value in both of the features. But here in SMC, we also consider those data points where we have value false in both feature value. So SMC is calculated as number of elements having both true values in 1, 1 plus number of elements having both 0 values, that is n 0, 0. Divide by number of both are having 0 plus number of elements having either 1, that is 0, 1, number of elements with true and 0, 1 and 0 and number of elements 1, 1. If you have noticed carefully, you would come to know that our denominator is nothing but set of all elements in a given data set, that is n. So again, let us calculate and understand SMC with the help of an example. This is my feature 1 and feature 2. Here we will calculate number of elements where we have both values as 1 and number of elements where both features are having value 0. Two instances where feature 1 and 2 both are having value 1 and 3 instances where feature 1 and 2 both are having value 0. And the total number of data set is nothing but 8. So 5 divided by 8 is nothing but 0.625. That is, these two features are similar 62.5%. And the amount of dissimilar information they do contain is D of SMC, which is 1 minus SMC. So 1 minus 0.625 gives us 0.375. So these two features 1 and 2 are containing 37.5% dissimilar or non-redundant information. So again, in this coefficient-based method also, we would like to have or we would have something called as threshold value to identify set of similarity. Next coefficient-based method is cosine similarity. So it is one of the most popular measure in text classification. Say if my attributes are not binary and if my data set is used for text classification, we must use cosine similarity information. Now, how to calculate cosine of any two feature x and y? Cosine of two features x and y is calculated as cosine of x comma y is equal to x into y divided by double modulo of x into double modulo of y. So this can be x into y is calculated as multiplying each data point or each data instances and taking its sum. X component is calculated as square root of sum of square terms of x. That means I will first calculate square of each data point for given feature x and I will add these squared terms and take square root of. Similarly, I will calculate y component. Say for example, feature x is given by one vector 24002130 and y feature is given as vector 2100321101. Now, in order to calculate x into y, we will multiply each component of vector element by element and we will sum them. So, first component of vector x is multiplied with first component of y, that is nothing but 2 into 2. Similarly, second component of x vector is multiplied with second component of y, that is nothing but 4 into 1. And likewise, we will keep on multiplying element by element and we will take sum of these values. So, we will take sum of these product. Okay, so product of these multiplied terms will give me x into y. Multiplication of each individual vector elements and their sum is nothing but my x into y. Now, in order to calculate this x component, we will take square of each term. So 2 square, 4 square, 0 square will be calculated and we will add these terms and we will add these squared terms of x and finally we will take square root of their sum. That is nothing but square root of 34 which is equal to 5.83. Similarly, we will repeat for y. We will take elements of y vector, we will square them individually, we will take their sum and finally their sum's square root is taken out which is equal to 4.47. Now, we will substitute value of x into y, x component into y component which is calculated as cosine of xy 90 divided by 5.83 into 4.47 which is equal to 0.729. So 0.729 is our final answer. So this cosine similarity measure or whatever answer we have got, that is 0.729, is measuring the angle between x and y vector. Remember, x and y are nothing but vector. So the angle between x and y vector is given by cosine of xy. So this value of cosine similarity 1 indicates the angle between x and y is 0 degree. So we take a cosine inverse of a given angle to find out the degree between these two vectors. So if this cosine value is 1, that means x and y would have same angle, that means 0 degree. So vector x and vector y, they are having degree between them as 0. But as you can see, their magnitude is same. Okay, so I can say that they are redundant feature. I can say feature x and y are redundant, or they are giving same amount of same information, or they are contributing same information. If cosine similarity is 0, okay, if cosine similarity is 0, then I can say x and y is having 90-degree measure. So if this is my x and this is my y, and this is 90 degree. Only when I have cosine of x comma y value as 0. So I can say that x and y are two independent features. I can also say that they do not share any similarity, and the term text data have no word in common between two sentences. If x and y are two different sentences, I must say that these two sentences does not have any word common in them. So coming back to our example where we have got cosine similarity as 0.729, we calculate angle of cosine as cosine inverse of 0.729, which is equal to 43.2. So if I would like to draw these two vectors, vector x and vector y, which are ultimately features but represented in a form of vectors, they are having 43.2 degree in it. Thank you everyone for watching this video. This is Munira Topia signing out.